My name is Elad, and I'll be presenting Self-Supervised Classification Network. This work is an IBM Technion collaboration and was co-authored with Leonid and Alex. We present a new self-supervised approach called Self-Classifier. Self-Classifier learns labels and representations simultaneously in an unsupervised manner. It is simple to implement, and despite its simplicity, we set a new state-of-the-art performance for unsupervised image classification. Additionally, it also achieves state-of-the-art comparable results for self-supervised representation learning. Self-Classifier is a type of contrastive learning model. Contrastive learning models learn useful representations by maximizing the similarity of two or more augmentations of the same image. What makes each model different is the way it avoids degenerate solutions. Over the years, many approaches have been suggested, from negative samples to two networks when one is the moving average of the other, and even external clustering. Self-Classifier is also a type of deep clustering method. Deep clustering methods learn parameters and cluster assignments simultaneously. Such a task is vulnerable to degenerate solutions as well, and most of the previous work avoids the trivial outcome by using some form of pseudo-labeling in a two-stage process. In contrast, our approach learns in a single-stage end-to-end manner using SGD only and without pseudo-labels. So we start off with no ground truth labels and no pseudo-labels as well. The intuition of our approach is the following. If we can classify two views of the same sample to the same class, then it is more likely that two different samples with the same ground truth label will also be classified similarly. So if you let x1 and x2 denote two augmented views of the same sample, then a naive solution will be to minimize the cross-entropy. However, an attempt to minimize that will quickly converge to a degenerate solution, such that all of our samples in the dataset will be mapped to a single class. In this work, we use two mathematical tricks to exclude degenerate solutions from the commonly used cross-entropy loss function. We propose to invoke two simple rules, the Bayes theorem and the law of total probability as follows. We plug these two new equations into the original cross-entropy loss function, and what this allows us to do is set the class distribution manually. So by simply setting it to be the uniform distribution, our new loss function no longer includes degenerate solutions that are also optimal in the sense of zero loss. Our approach is very simple to implement, just a few lines of code, and does not require any architectural changes to the standard classifier. We set a new state-of-the-art performance for unsupervised ImageNet classification, and additionally, training a supervised linear classifier on top of the frozen learned features yields comparable to state-of-the-art results for self-supervised representation learning, despite being much simpler to implement. So why does it work? In the paper, we show mathematically that with our proposed loss function, each class has at least one sample with non-zero probability and vice versa. So in practice, classes without any assigned samples are simply not an option. So we finish off with some visualizations. These are high accuracy classes predicted by Self-Classifier, an ImageNet validation set. The predicted classes capture a large variety of different backgrounds and viewpoints, showing that Self-Classifier learns semantically meaningful classes. For completeness, we show in red some of the low accuracy classes as well. We see that even for low accuracy classes, semantic grouping is reasonably good. A lot of the misclassified samples are due to subclasses from the same superclass that are clustered together. For example, different types of birds, monkeys, or fruits. Thank you for listening. The code is available on GitHub, and I invite you to post a session if you have any questions.